All right, good morning, everybody. Let's go ahead and get started. So I promised everybody that we would take a look at the silver mirror demonstration. So I'm going to hold to that today. And I also said that I'd give the flask to anyone who scored a perfect score on the exam. And so I have one to make and one to give out. So
you mean that 104 you mean?
So, what reagent? Let me finish the question, Jason. Yes, Tollin's reagent. Tollin's reagent is what we're going to be using, so we got to make Tollin's reagent. What does Tollin's reagent test for?
Aldehydes.
The presence of an aldehyde, right? And so what it does, when it does that, is it makes a silver mirror. So the first thing we've got to do is make Tollin's reagent. Does anybody remember what was in Tollin's reagent, roughly?
Silver.
Yeah, so we got silver plus, right? So I've got a 0.1 molar solution of silver nitrate right here. And I need to put, first I need to put down a paper towel, just in case I get a little messy. Anybody know anything about silver nitrate? This is what they, I don't know if they still do it or not, but at least when I was born and when my siblings were born, newborn babies, they would put silver nitrate in their eyes, and newborn babies would have this brown circle around their eyes because it would, it's a bactericide, and so it would, you know, the whole birthing process, there's issues, and so they would use silver nitrate for that. So what I need is 30 milliliters of silver nitrate. So I'm going to measure out a little silver nitrate here. We'll call that good enough. And I'm going to place it into the flask that we're going to silver. We're going to silver a 125 milliliter flask. Now, the silver nitrate by itself won't do anything. It's got to be under basic conditions, so we have to make it basic. Okay? And we're going to add potassium hydroxide. But you might remember from Gen Chem that silver and hydroxide forms a precipitate. Well, I don't want to precipitate. Everything's got to be in solution. But what it turns out to be is that I can add some ammonia to this, and it will make everything soluble again. So what I'm going to do is I'm going to add a little bit of ammonia to start with. Now this is ammonia in water, which has a little bit of hydroxide in it, so it will form a little bit of a precipitate when I first add it. Start to see it form that brown precipitate. And I'm going to continue to add ammonia until everything goes into solution. Back into solution, there we go. Whew, the ammonia smell. All right, now I'm going to add some potassium hydroxide. So this is about a 0.8 molar solution of potassium hydroxide. I'm going to add, let's see, I add about 15 milliliters of that. Roughly get, and there I go. That's why I have this paper towel. What do you think is going to happen when I add the potassium hydroxide?
Chemical reaction.
It's going to do this. It's going to what?
Reaction.
Going to do a reaction, that's true. I'm going to form pretty much so nothing. And why nothing? Because I added the ammonia. Right? So I added a little excess ammonia to that. So we're good. And so now we have the Tollin's reagent. So now I need to oxidize something. I need to oxidize an aldehyde. And what we're going to use is dextrose. Dextrose is the same thing as glucose. It's a oxidizing sugar, or it's a reducing sugar, excuse me. It's going to get oxidized. And it's really sits as the hemiacetal form in solution, but it does ring open into the aldehyde, and so it's the aldehyde piece that's going to do the chemistry for us. So I'm going to add about 6 milliliters of that. And it's going to start turning kind of a color on me. shake it for a while. Why am I shaking it?
Speed up the reaction.
Nah.
Because it looks cool.
Because it looks cool? I gotta get it all over the flask. I want the flask to look like a mirror, right? I just let it sit in the bottom, just the bottom would be mirrored. So, right now I'm just, you starting to see the formation of a mirror maybe?
It's shiny.
It's starting to look shiny, isn't it?
Uh-huh.
Look real shiny. And it's gonna look even shinier here in just a few minutes. This is how they used to make silver Christmas tree ornaments. Have a glass blower blow whatever you wanted, you know, a ball or whatever. And then they'd put Tollens reagent in it and they would shake it up and they would make a,
Wasn't that thing clear just a minute ago?
it was. What is it now?
Looking like a mirror.
Looking like a mirror. I can start to see my reflection, for better or worse. So I have made a silver mirror. I'm gonna do just a couple more minutes. I want it to be nice and coated. I'm starting to get sore. I asked Thomas, Columbia, to come down. Thomas did this with me yesterday. He had fun with it, I think. Columbia came down because she's never seen it before. Columbia does research in my lab, so she's doing her capstone this semester with me, and so I thought I'd have her come down and take a look at it. But also I need somebody to carry all this junk back up. And it turns out that what's in there right now, I'm gonna pour this out. If I let it sit for very long, it actually forms an explosive silver nitride by reacting with the nitrogen in the air. So I don't want that to happen either, right? So Thomas is gonna carry it up. He's going to dispose of it properly so that we don't have any boom boom. So what?
So if we start seeing sparks, you should be running?
No sparks, just boom.
I don't like it when it goes boom.
You get the natural selection right here.
I've actually had a couple of explosions during my time as a chemist.
Oh,
That's,
Not doing this. But I gotta rinse it out real good because we don't want any silver nitrate. Silver nitrate will turn your hands brown.
nice. That's starting to see through.
Get the water out of it. Now, what I will tell you about this, it looks like there's a lot of silver there. It's about a dime's worth of silver. It's just a real thin, tiny coat. Okay, you can't really see through it. If you hold it up to a really bright light, you'll be able to see through it. You can see your reflection. It kind of distorts my reflection. Maybe that looks better, maybe it doesn't. But you can't, put a bunch of pencils in it or whatever, it'll scrape it off. But what you can do is you can take some dilute black paint or something like that and put in there and kind of swirl it around and let it dry, and that'll give it a protecting coating. And so that is a silver mirror, and that is how we would have determined that we had a aldehyde in that, or a sugar that can open up into an aldehyde. And so with that, Colton, congratulations. Yeah. And so I made another one just in case I messed up. So if anybody ever wants to make their own Christmas ornaments, come to the lab, bring your own glassware, we'll have fun.
Promise?
Do I promise?
Yeah.
Yeah, maybe I do. Maybe I'm telling a little bit of a
Yeah,
lie.
it's a good time.
Maybe I should be telling a little bit of a lie then. You're gonna carry the
Yeah.
part that you said was for you. you if you'll carry that. All right, good deal. Thank you both.
Yep. Godspeed. We can both.
No, I'm just going to trash. It's fine. Oh, wait, Columbia. All right, so y'all have seen the silver mirror. I will, for the recording, all right? And I'm going to pass this one around. Y'all can take a look at it. Don't stick a pencil in it, please. Feel free to take a look at your reflection in the mirror. Okay? So today is the last day of class. Tomorrow afternoon, around, what did I say, 5:30, there will be a final review session. I will post exam 3 on Canvas as soon as I get back from class. And so again, let me just reiterate, you all need to really focus on those old exams for the final exam, okay? And so if you're not happy with the grade where you're at right now, you've still got the final exam, and I'll take the better of the 2 grades. So last time we were talking about carboxylic acids. I'm going to go through this all pretty quick. We talked a little bit about nomenclature. We talked about the fact that there's a lot of common names in carboxylic acids. I am not going to hold you responsible for the common names on the final exam, with the exception of acetic acid, okay? You all need to know that acetic acid, which is also known as ethanoic acid, what it is. It's vinegar. That one's so common, okay? We talked the other day about the physical properties, the fact that these form these hydrogen bond dimers. We talked about the fact that you can have carboxylic acid soluble in water, but as you add more and more carbon, it becomes less and less soluble. We talked a little bit about that. We started to talk about lipids and how this was relevant for a lot of your majors. Cell membranes are composed of lipids, but the fats that you cook with are also composed of lipids. So for those of you in the nutrition areas, you at some point will be talking about lipids and cooking with them and doing different things, right? So lipids are very important, and we had the so-called polyunsaturated fatty acids, and of course we have saturated fatty acids and everything kind of in between. We also talked about the fact that most of your natural fatty acids all have the cis alkenes, but there are trans ones available. These are usually man-made, usually by accident, and then they're considered less healthy for you than the polyunsaturated fatty acids. We talked about the acidity. We talked about equilibria a little bit. We talked about an equilibrium constant. And then we talked about how the equilibrium constant can be converted into an acidity constant. So we discussed that. And then we talked about the fact that these are typically very small numbers, and so they're very difficult to work with. And so chemists take the negative log of those small numbers so that you're dealing with numbers that are easier to deal with on a regular basis. And we talked about the fact that carboxylic acids have a pKa of somewhere between 4 and 5, usually. But then we also talked about things that can affect the acidity, right? So electron withdrawing groups attached to the carboxylic acid can change the acidity. So you can see for acetic acid, right, going from 4.6 all the way to trichloroacetic acid, replacing all of those hydrogens with chlorine really has an impact on the acidity. We talked about being able to use this to our advantage so we can separate acids from non-acids, or things that have lower acidity, I should say. And so you can separate these things by taking advantage of this reaction, because while carboxylic acids themselves, if you don't satisfy that 5-carbon rule, typically you're insoluble in water, and this one's slightly soluble. When you make the salts, especially the sodium salts, they become quite soluble. So sodium benzoate, you can get up to 60 grams of sodium benzoate into 100 milliliters of solution pretty easily. And so you can use this to your advantage to separate acids from a variety of things. We talked about the reactions of carboxylic acids, the fact that you can take a carboxylic acid and make a carboxylate, as we just showed in the previous slide, but that these can also behave as nucleophiles and do SN2 kind of reactions and make esters, right? So we talked a little bit about that. And then we also talked about the fact that we can do the same reaction using this setup. This is a one-step reaction. What was the name of that reaction? Anybody remember? Yes, the Fischer esterification, and it's where you take a primary alcohol or methanol, you take a carboxylic acid, a little bit of sulfuric acid, and you can make the esters quite easily. This is methyl benzoate. It's an ester. It is the scent in snapdragons, the flower of the snapdragon, and it's used as a pollinator attractant. So flowers make this to attract pollinators so that they can come and get the pollen and carry it on to other plants, right? We talked about carboxylic acid derivatives. We talked about acid chlorides, and how the fact that you can make those from carboxylic acids using this reagent called thionyl chloride pretty easily. We've talked about thionyl chloride in the past. Thionyl chloride will react with alcohols to make alkyl halides as well. So it kind of does the same type of chemistry here as well, and it converts a carboxylic acid into a so-called acid chloride, which are very reactive and can react with a variety of nucleophiles. We talked a little bit about that. All right, so then we got into amino acids, and we talked about alpha amino acids. Those are the ones that I'm going to hold you responsible for. We talked about the fact that if R is something other than hydrogen, these all are chiral, right? We call them L amino acids. That's how you're going to learn about them in biochem. But all L amino acids are of the S stereochemistry, except for cysteine. Cysteine actually has the R absolute stereochemistry, even though it's an L amino acid. And it's because the sulfur takes priority over oxygen when you're doing those Cronenberg-Prelog rules that we learned about when we did the chirality chapter. Okay? We talked about this idea that you have a carboxylic acid and you have an amine. So you've got a good acid and you've got a good base. These should react with each other, and in fact they do when you put them into solution. Amino acids will exist as a Zwitter ion if you just put them into pure water. So if I took a flask of pure water and I put an amino acid in it, it would exist as this Zwitter ion. Okay? Zwitter ion means that you have overall the molecule is neutral, but it has charges. It has an equal number of positive and negative charges to it. Okay? So it's overall neutral, but there are charges, right? So positive clearly cancels out negative, and we call these Zwitter ions. Okay? I mentioned to you that you need to know the structures and the codes of these amino acids, and I realize that the final exam is on Monday. This is something that I encourage you to put in your notes. Okay? You should copy down all of the amino acids from table 18.1 into your notes so that you have them. And I will hold you responsible for the 3-letter code. So in a problem, if I said GLY is which of the following amino acids, that would be glycine, and you might have to look up the structure, okay, or something along those lines. So again, keep this in mind. But the table breaks it up into the nonpolar side chains, things that won't ionize, things like hydrocarbons and et cetera, et cetera. But there are also polar side chains. So things that have polar groups are also common. These are very, very important. You also have acidic side chains, aspartic acid, glutamic acid, cysteine, tyrosine. These are all reasonably good acids. And then, of course, you have basic side chains as well. So arginine, histidine, lysine, so on and so forth. Okay, so that's about where we finished up last time, if I remember right. So we will jump in right now. And so let's suppose we have a solution at pH 7. So it's just pure water. We've thrown in an amino acid, and we would expect to have a Zwitter ion. Okay? But then you come along and you add some acid. That's what H plus is depicting here. So let's say Selena comes in and she adds just a dropper full of concentrated sulfuric acid to the reaction mixture, or to the solution. What would happen in doing that, the nitrogen already has its octet filled. It doesn't have a lone pair of electrons anymore, but the carboxylate could pick up that proton. And so at at low pH, high acidity I should say, amino acids are typically positively charged.
Isn't it like something in the sixes?
4, 7.3.
7.3 is a little low. 7.4 is close. 7.4, 7.5 is
Yeah,
about
around
that area.
Around the Goldilocks ages?
Pardon?
Goldilocks.
Goldilocks?
Not too acidic,
Oh,
not too bad.
I got you. Okay. Yeah. So your body has buffers that maintain that pH, and that's very important. If your pH of your blood changes by much more than a tenth or 2/10 of a pH unit, you'll die. And you'll die because the charge state of your amino acids will change. And when that happens, they change shape. And when they change shape, they change function. They don't behave like they're supposed to anymore. pH is the most important thing in medicine. It really is. Doctors may disagree with me, but when you go to the doctor and they give you a shot in your veins, they have to make sure that it's an isotonic solution so that they don't dehydrate your cells, and they have to make sure that the pH is right so they don't screw that up. Okay? It's very, very important that people who inject things into your body are injecting things that don't do this type of stuff. Okay? So let's take a look at a table. This again is a table out of your book. Okay, you'll see the amino acids, so alanine, arginine, asparagine. They did this alphabetical, it looks like. You'll see the pKa of the alpha COOH, so this is the pKa of the carboxylic acid. What can you tell me about the pKa's here versus what I told you a typical carboxylic acid pKa is? They're lower. Why are they lower? I told you that a pKa of a typical carboxylic acid was where? 4 to 5. And these are all below, well, they're not below 2, but they're below 3, right? Why are they lower?
Nitrogen is kind of electronegative.
That's right. The alpha nitrogen is electronegative, especially if it's positively charged, right? And so that pulls electron density to itself. That lowers the pKa. Just like when we took acetic acid where we replaced one of the hydrogens with the chlorine, what happened to the pKa? It went down, right? Nitrogen is electronegative. It's a little further on the periodic table to the right, correct? So it has the same effect. You'll also see that the pKa of the ammonium ion is somewhere around 9, somewhere between 9 and 10. Okay? So you'll see that it does differ a little bit. And then you'll see that some of the side chains also have a pKa. So arginine has an ionizable group, and it has a pKa of 12.48. Aspartic acid, its side chain has a pKa of 3.86, so on and so forth. You all can look this kind of information up. There's also this PI, this so-called isoelectric point number. Can you tell me anything about that? What is the PI?
What's the name of it?
The isoelectric point.
I always have the question. Should we write this in our notes?
Like the average.
So these numbers I will give you if you need them. I wouldn't worry about them. You need to know how to use them though.
Do the average.
Average of what?
All the numbers that are.
So if I took aspartic acid and I took 2.1, 9.8, and 3.9, and I added them up and I averaged them, would it come out to just about 3?
No.
No. So it's not the average of all the numbers, is it?
Is it the average of the first two?
You tell me, is it?
I can't really see the numbers from here.
All right, so the first two are 2.1 and
No.
9.82. So if I took those two numbers and I averaged them, would I get 3?
No.
Maybe
No.
if it has a side chain, then it will be the average of the carboxylic
Isn't the
acid
first
and the
one
side
number?
chain. But
Ah,
if
very
it's-
good. So if I took this number, 2.1 and 3.86, and added them and divided by 2, quickly do that math for me. What does that come out to be? You can use a calculator. So take 2.10, add 3.86 to it, divide by 2. What do you get?
298.
Pardon?
298.
You get 298. That's right. Okay? The isoelectric point is the pH at which the amino acid is a zwitterion. It is electrically neutral. Okay? So if I take alanine and I adjust the pH of the solution to 6.11, it would be a perfect zwitterion. If I took aspartic acid, put it in solution, and I adjust the pH to 2.98, it would be a perfect zwitterion. It would have exactly one positive charge and one negative charge.
Can you repeat what, you said the definition of isoelectric point was?
Isoelectric is that pH at which your amino acid is a zwitterion. Okay? And that has implications in terms of what you all can do in the lab. We'll talk about that in a moment. All right? But now let's look at lysine. So here for aspartic acid, Jason said I take the pKa of the carboxylic acid and I take the pKa of the side chain and I average those, and that gave me exactly that number, and he was correct. Is that true for lysine?
No.
No, it's not. What two numbers are we using for lysine?
The
The second and third. So I take 8.95, 10.53, I add them together, divide by 2, and I get 9.74. The isoelectric point, you always take the two groups that are closest in pKa and you average them. Right? So when I look at lysine, 2.18, 8.95, and 10.53, these are closer to one another. You take the two groups that have the closest pKa's, you add them together, and you divide by 2. Okay? That's the isoelectric point. Now, if all I've got is two groups, 2.28, 9.21, I take those two, I average them up, and that's what it comes out to be. Okay? I can guarantee you there will be an isoelectric point calculation on the final exam. Okay? I will give you everything that you need to figure it out, but you have to know how to figure it out. Okay?
So it's the two numbers closest to each other and then add them and divide them by 2?
Yep, just do an average. Yep. So here's an example. Now these came from a different book, so the values are a little bit different. So don't worry too much about those slight differences. But here we have the amino acid alanine. I know it's alanine because of the methyl group on the side chain. It just has a simple methyl group there. It is chiral, right? This carbon has a methyl group, a nitrogen, a hydrogen, and a carboxylic acid, so 4 different things around it. The pKa of this group is 2.34. The pKa of the ammonium cation is 9.69. So we take 2.34 plus 9.69, divide that by 2, and I get the Pi value of 6.02. If I take lysine, right? The carboxylic acid is 2.18, the pKa of the amine is 8.95, and the side chain is 10.79, right? So I have to average these two because they're closer together. Remember, a zwitterion is going to have a negative charge and one positive charge. As this is drawn right now, it has two positive charges. It's not a zwitterion. So I have to figure out where would the pH be to where only one of these groups would have the positive charge. And I average those two. Okay? So at pH 9.87, it's already going to have a negative charge. This is going to be deprotonated. Okay? But at this pH, only one of these groups will carry a positive charge, not both. So you just take these two and you average them. Just like here for glutamic acid, this and this have the closest pKa values, so those are the ones that I'm going to average. And you're going to find that at pH 3.22, this would be a perfect zwitterion. Okay? So, if you had lysine floating around in your blood, and it has a Pi of 9.87, what do you think the overall charge is of lysine floating around in your blood that has a pH of 7.4?
What is the percentage?
Negative. Wait.
Can you repeat the question?
What's the charge on lysine if it's floating around in your blood? It's lysine by itself.
Positive 2.
Is it positive 2? The overall charge. If the blood is pH 7.4, is this going to be protonated or deprotonated?
Deep.
So that's going to be minus, right? And what are these going to be? They're both going to be positive. So
Okay.
2 positives plus a negative is
Positive 1.
positive 1. So free lysine floating around in human blood serum is going to have a positive 1 overall charge. Okay?
Can you repeat how you got that? Okay.
How I got what? The fact that it's overall positively charged?
Yeah.
So at pH 7, the carboxylic acid is going to be completely deprotonated because it has a pKa of 2.1, 2.2.
What does that mean?
That means it's going to be deprotonated. Your blood is more basic than this, right?
Yeah.
So it's going to be protonated. But this is going to these are going to remain positively charged because the pKa is higher than the pH of your blood. So these are still going to be positively charged. So a positive plus a negative is overall 1 positive charge. See how that works? Okay. So I want you all to get together on a piece of paper, write your name, work in groups, and I want you to calculate the PI of the following amino acids, okay, using the values in the book. So I want to write these down, and then I'll take you back to the table. So you're going to calculate the PI for asparagine, for arginine, for serine, and for aspartic acid. All right? So I need you all to calculate the isoelectric points. They're already up there. Don't just write them down. Show me the calculations.
You said work in partners, do we turn in one paper or 2 papers?
Everybody needs to turn in their own paper.
So you said
Everybody should get full 20 points on this, right? The answers are up there. But I want you to do the math. Everybody see this over the flask?
That's fucking Josh.
I don't know. I don't know if it's plastic.
That would just be that 2.02 plus 8.80.
That's rubber, but no.
you expect when I come out?
I don't.
You expect when to come out? I don't feel like going autistic on my work. The only thing I didn't grab when I left my dorm. I love losing things. So all we're doing is essentially, each one of these we use in to get.
Serine. S-E-R. My handwriting is terrible, I know.
Which one's worse, yours or mine?
Definitely yours.
Yeah, you might wanna take a few steps back, so.
First professor told me that.
I like it on.
He's like, don't even comment on it. Sorry.
That's why I was about to say, I know mine looks like ancient Greek. Or some kind of forgotten language.
You take, I think you take Michael Vera.
I'm sure I'm gonna wake up every morning. I woke up 4 minutes.
Yeah, she does. Poor girl.
It was.
I passed from the first try, so it's really not that bad.
Is this what you have?
About 2 more minutes. I need you to wrap it up, and then we'll pass them over to the left so I can take them up.
I think it just shows the smallest number.
Yeah, we just got more farming.
This is like not more than
I enjoy it. I wish I
At the two closest ones.
I have to go back to the house and get Nope. To what? Laura and Marie's wedding. I keep forgetting. Yeah, last one. It's January 7th. Also because I know these are the only socks that won't like slip down with my right knees. I don't feel like having a surgery. It's like right before
All right, folks, pass it to your left.
I have to go like a while and a half to get
Man said be quick, be quick.
Jason, I need to buy you some bigger paper.
I'm trying to not consume trees.
Okay.
Trees, girls.
and so.
It's like a fringe on. No. Come on, aggravating. Yeah, girls. I taught you better than that. I'm just saying, if anything, my mom has expressed it. Take your friend.
I didn't either.
You all got yours?
Mine are right here.
Oh, okay.
I thought I taught you better than that.
Is that both of them? That's okay.
Yeah, she did do 30 on that. Yeah, she did. And you didn't tell her that?
No, should I?
Be like, hey, ding dong.
It is. We can't see.
Actually, you
All right.
should screenshot it or something. That's nice.
Who's she?
Final quiz you all have to do. It's done. All right, so why is this important? This allows us to separate amino acids, and we can even separate peptides and proteins, or polymers of these things, based on isoelectric point, okay? So if you think about it, right, if I could take a paper strip, and if I could hook it to a battery, right, so we've got a cathode and an anode, right? So you all remember that a cathode means that it attracts positive things to it, which means it's negatively charged. And an anode means that it attracts negative things to it, which means that it's positively charged, right? And so if I put this paper strip in the middle, and between these two solutions, and I put my amino acid right, or a set of amino acids, let's say I've got more than one amino acid, and I put them right here, and things that are negatively charged should move towards the anode, and things that are positively charged should move toward the cathode, right? That makes sense, right? If you're negatively charged, you'd like to move towards something that's positively charged. This is called electrophoresis. This is a technique you'll learn in biochemistry. You may learn it in your medical laboratory science classes as well. It's a way in which we can separate biomolecules that are charged, okay? There are a lot of different types of electrophoresis. But what about if I have a mixture of amino acids that has half of them are negatively charged and half of them are positively charged, right? They would just migrate towards their respective electrodes that they like. But they may not separate from themselves, right? So if I have 3 or 4 amino acids that are overall negatively charged, I still want to separate those, right? Well, there's a trick we can do. And the trick is we can take this paper strip and we can make it into something else. We can make it a gel, okay? And in that gel, we can actually put a pH gradient. So we can change the pH from 0.0 all the way to 0.1 or whatever. We can change the pH, okay? So now so there's a pH that goes from, let's say, pH of 0 to a pH of, I don't know, 7 or 8, 9, 10, whatever the number is on these gels, okay? I can put my amino acids in here. I can hook it up to the car battery, so to speak, and I can let it run. What's going to happen? The negative ones are going to go towards the positive electrode. The positive ones are going to go to the negative electrode. But then what's going to happen? At some point, amino acids will stop moving. Why?
It has a sweet spot, the isoelectron.
That's right. At some point in this strip, the amino acid will get to where the pH is equal to its pi. And when that happens, it becomes electrically neutral. When it's a Zwitterion, is it going to be attracted to the positive electrode or the negative electrode? Neither. It's going to just stop. So this is called isoelectric focusing. Okay? And it's a technique that you will learn in biochem. It is a technique that I am sure you will learn in medical laboratory sciences. I don't know if they talk about that in the nutrition areas. Certainly you would deal with this in forensic biology kind of things, right? Because you separate proteins and you separate biomolecules to try to determine what's happened at the crime scene, et cetera, et cetera. This is a technique that uses that, okay? And so it will move until the pH equals the pi, and it will allow you to separate these amino acids, okay? It's a very good technique for that. All right. So we've talked about amino acids, but amino acids by themselves, I mean, they're useful. They're, you need them. You all take essential amino acids in your diet or in supplements. But your body actually takes these amino acids and makes what are called peptides and proteins, polymers of these amino acids to make structural things. Your muscles are proteins, okay? There's all kinds of peptides, small proteins that float around in your blood, okay? And so what is the difference between a peptide and a protein? Size, okay? We are not going to have enough time for me to get to the protein piece of this before class is over today, but we're going to talk about peptides. So generally it is considered if you have between 2 amino acids linked together and up to 50, we call that a peptide, okay? If you or anybody in your household or your relatives or friends are diabetic and they take insulin, they are taking a peptide as a drug. Okay, insulin is a peptide. It's a peptidic drug. Okay? And by convention, when we link these amino acids together, this is the linking together of glycine and alanine. So here's alanine, here's glycine linked together through what we call an amide bond. Okay? This is called a dipeptide. Di for 2, peptide being less than 50 amino acids. Okay? And we would abbreviate that as gly-ala. Okay? Notice we always start with the nitrogen terminus first and we end with the C terminus, or the carboxylic acid terminus. So it's always in the C when we write these things down. This is what a ball and stick model would look like if you built one. Okay, so Selena, if you took your model kit and you built one, this is what gly-ala would look like. Okay? So what's important? Where do we start? We start on the nitrogen terminus, and we end in the so the acid side or the carboxylate. So I always say it's in the C, left to right. That's how you write this. Okay. So here's a tetrapeptide. Can you all see the 4 amino acids? What's this one? That's glycine. That's serine. That's phenylalanine. And that's glycine again.
So you just spell these off all the
I know because I've done this a lot. Yeah. I do this a lot, right? So, the easiest way to do this is to count the side chains. There's a hydrogen, there's the CH2OH, there's the CH2CH benzene ring, and there's another H. You got 1, 2, 3, 4 side chains off that alpha carbon. Okay? So I know that 4 amino acids have come together to build this, right? Now, the peptide bond is also known as an amide bond. In this class, we've always called them amides, but you can see that the carboxylate, the carbonyl of one amino acid, is now reacted with the nitrogen of another amino acid, and it's formed a new functional group, right? This is the amide bond. So if you think about, let's make it very simple, and I'm not going to draw it completely correctly or completely charged. So there's glycine, and let's say we want to put another glycine together to make a dipeptide. If I just throw these things together, would that happen? No. The base would react with the acid and you'd get a salt, right? Your body has enzymes that do this chemistry for you. Okay? You're going to learn about that in biochemistry. Okay? But amino acids get charged on the things called tRNA. Then you have an enzyme that takes those TNAs that are charged with the amino acid and it starts to link them together and make these polymers. And it can do it very, very efficiently. Okay? But it has to activate the carboxylic acid because ultimately to make the amide, what's missing? What do I need to write out here plus what?
H2O.
That's right. It is technically a dehydration reaction. Your body takes the amino acids and spits out water. You all may have heard about metabolic water, that there are some animals that don't really need to drink a lot of water because they produce enough water through this process to sustain themselves. Okay? So your body actually does do this. So as you take a carboxylic acid and an amine, you condense it into an amide by the elimination of water in the reaction. Okay? Now, it turns out that the amide bond has a very special resonance structure. The nitrogen atom on the amide is resonance delocalized into that whole amide bond. Okay? And this gives the amides very special character. Okay? It turns out that the amide nitrogen, this is actually sp2 hybridized. Does that look like sp2 hybridized as I've drawn it there? No. sp2 hybridized, we always said had at least one pi bond, right? Well, it's the resonance structure that actually does have the one pi bond. Your amide bonds really look more like this than like this. Quite a bit more like this than like this. Okay? And so, can we rotate around carbon? Can we rotate around double bonds? No. The amide bond is restricted. And that's very, very important. And the amide bond is also very strong because of this resonance structure. Okay? If this resonance structure didn't exist, when you would place protein in water, it would almost instantly degrade into its amino acid constituents. It's not very good for life. Right? We're water-based, we're carbon-based, we've got amino acids. These things have to be fairly strong, right? And the amide bond is strong, and it resists degradation, which is a good thing. Okay? As you start to put multiple amino acids together, because this is a planar bond between here, okay? There is no free rotation, as you might expect. it means that the side chains will actually be on opposite ends of the chain. One will go behind the plane of the board, one will come out of the plane of the board. Then the next one will go behind, and you get this alternating in and out of these groups. And that's because there's no free rotation around that amide bond, and they're all of the same absolute stereochemistry. Okay, and so you'll have this, as they've drawn it here, kind of up and then down. If you think of this as the plane of the peptide that we're talking about. Okay, and you'll notice by looking at all of the, so here's an amide, right? There's the nitrogen, there's the carbon, there's the oxygen, there's the hydrogen on the nitrogen. This is planar. These 4 atoms all lie in the same plane. Okay, and that results in these side chains being up and down. Okay, this particular peptide is glycine, serine, phenylalanine, glycine. So there's the glycine, there's the alanine methyl group, the serine, right? Because that oxygen that's an oxygen there. Then the phenylalanine and then glycine again. So there is another type of bond that gets formed in proteins and peptides called disulfide linkages. Okay, so you can have one strand of a peptide or protein, you can have another strand, and where there are cysteines, these things can actually form sulfur-sulfur bonds. Okay, this turns out to be very important. So there are some structures in proteins that have to be held permanently in place. And the way that Mother Nature does that is by using covalent bonds. Why does she use covalent bonds? Because they're strong. They resist change, right? And so you will find if you look at something like insulin, it's actually held together. The 2 strands of insulin are held together by these so-called disulfide bonds or disulfide linkages. When we take 2 cysteine molecules and form this disulfide, we call it cysteine. Okay, change the name. So 2 cysteine units come together to form what is called cysteine. So the disulfide bond makes the amino acid cysteine. Okay, so you just kind of drop the E from the name. Okay? So you can take 2 cysteines, and if they're close enough to one another, they can be oxidized to give cysteine, or the disulfide linkage. Okay? How do I know this is oxidation?
I know if it's oxidized.
Yeah, how do I know that going from cysteine, or 2 cysteines to 1 cysteine,
Lose hydrogen.
I'm losing hydrogen, right? And in organic chemistry, typically when you lose hydrogens, you're oxidizing something. But these things can also go in reverse. Your body has reductants that serve the purpose of breaking the disulfide bond so that you can get the protein to open back up. Okay? It's complicated. You're going to learn about all this fun stuff in biochemistry. Okay? But that's a reduction. So cysteine is redox active. It can be reduced and it can be oxidized. And this has very, very important consequences. If you've ever gone to the beauty salon and gotten a permanent, or your hair straightened or curlied up or whatever, you've used this chemistry. Your hair has a lot of cysteine. It's cysteine rich. In fact, in the old days, that's how chemists got cysteine. They would literally go to a barber shop. They would gather up all the nasty hair. They would then take it and hydrolyze it and isolate the cysteine from it. Your hair is very cysteine rich. Okay? And so to straighten one's hair, okay, you reduce the disulfides that are present, and it breaks them and it straightens it out. Then what do? They take your hair and they wrap it around something that you want it to take the shape of, and then they put another solution on there that they probably call a fixer, but it's just an oxidant. And it oxidizes the cysteines back to the disulfide, but now that you've changed the shape, you've made different cysteines be closer to one another. And when you oxidize it, then it becomes quote unquote permanent. Now this isn't genetic, right? So it grows out. But it is permanent in the area where you made these alterations. So this is a practical explanation for things that some of you may or may not do. It used to be a common thing back when I was a kid. People would go get permanents all the time. I don't think people do that quite so much anymore. But, so if you've ever been to the beauty salon and you've smelled that kind of rotten egg smell when they're doing a permanent, that's the reducer. And it contains thiols, and they stink. Thiols have an odor. And so that's what they're doing. They're breaking the disulfide bonds and straightening it, and then wrapping it around something, you know, curler, soda can, whatever, and making the new bonds. Okay? So let's look at some other real things that might be of importance that have these disulfide bonds. This is the molecule known as bovine oxytocin. Okay? You'll notice it is cysteine, tyrosine, isoleucine, glutamic acid, arginine, cysteine, proline, leucine, glycine, and instead of having a carboxylic acid at the end, it has an amide. Okay? But this is bovine oxytocin. What does bovine mean? Cow. This is oxytocin that's isolated from cows. Okay? You'll notice it has a disulfide bond, so it forms this cyclic structure that you can kind of see here. Okay? So these two yellow ones are the sulfurs. And so it makes this cyclic structure, and then it has this other piece that hangs off of it. Okay? Does anybody know what oxytocin is used for?
Give it to women after they give birth.
They do. And why?
It helps with contractions, stop the bleeding.
It might do that.
I know it produces those contractions, but also helps with the secretion of milk.
Yep, it does. Yeah. So it can help with contractions, and it can help. Now, when you go to the doctor, if you ever go to the doctor and they start administering this to you, they're not going to call it bovine oxytocin. They call it Pitocin. It's the brand name. But that's what it is. It is derived from cows. The structure is, they no longer, I think, harvest it from cattle, but they synthetically make it in a laboratory using bioengineering techniques. And so, yeah, so this really helps with, so if a woman is having trouble with contractions, they will give her a Pitocin drip that helps intensify the contractions, and it also allows the milk to come in, okay? So it's a very useful thing, but it's a protein, or it's a peptide. What do you think would happen if you broke the disulfide bond? Would it work?
No.
No. You got to have the disulfide bond there, right? So it's got to have that structure, or it doesn't work right, okay? This is conotoxin G1. This one has two disulfide bonds. So this is glutamic acid, cysteine, asparagine, proline, alanine, cysteine, glycine, arginine, histidine, tyrosine, cysteine, and it's an amide at the end as well. This is a toxin from the fish hunting cone snail, right? And so it's paralytic. The cone snail will inject the fish with this. It paralyzes the fish, and then they can consume the fish, right? And so this is a protein, or a peptide, excuse me, that blocks the nicotinic choline receptors and doesn't allow muscle movement anymore. Okay, so it's a very potent toxin. But if you have any so if this happened to be connected to this sulfur and this one connected to that sulfur, it wouldn't work. It has to be this particular type of disulfide bonds formed for this to work. It's a venom. Okay? So let's talk really quickly about how we can determine the structure of peptides. So, you know, you're going to learn in biochem, you're going to learn a lot of proteins, you're going to learn of peptides. At some point, some scientists had to sit there and determine what it was, right? These things just don't magically fall from the sky. There was a lot of work that went into this. And back in the day, you could get a PhD by determining the structure of an unknown protein. Today, we can determine the structure of an unknown protein in about an hour. Technology has gotten a lot better, okay? But today, we still kind of have to do the same thing. We just have better technology to do it, okay? But I'm going to share with you the old way, okay? So let's suppose Colton got a structure, or got a sample of an unknown protein. I don't know, from some snail or something we found in the joint, okay? And he wants to know what that protein is. The first thing that he has to do is do an amino acid analysis, which is to find out how many amino acids are actually there and what they are. And what he would do is he would take that sample and he would put it in hydrochloric acid and he would boil it. And he would completely break that protein down into its component amino acids.
how would you know, like, do you wanna know, like, the single chain that is recurring, or like all of the recurring ones?
Well, you wanna know it all eventually. But the first thing he's gotta know is, okay, I've got a sample of a protein, at least, I need to know at least what amino acids are there and what ones aren't there. Right, so that's the first thing you gotta start with. And so he's kind of a synthetic, it's kind of a synthetic stomach is to take it and put it in hydrochloric acid and boil it. And so it breaks it down in just to its amino acids. And so he'll take that and he'll do an analysis, we're not gonna talk a lot about that, and he'd come up with, oh, I know this has these amino acids and it's got this number of them, okay? But you still don't know how they're connected, right? So he does the amino acid analysis. Then he's going to do the terminal residue analysis. He's going to find out what's on the ends of this protein or this peptide, okay? And the first thing he's going to do is going to do what's called an Edmond degradation, which tells you what amino acid is at the N-terminus. Okay, he adds some reagents, and it will actually cut off that one amino acid only at the N-terminus. And he'll analyze that. He'll say, oh, I know what the N-terminus is, so I know where I'm going to start. Right? Because we always write these out from the N-terminus to C-terminus. He's then going to take an enzyme called carboxyl peptidase, and he's going to add that to his sample, and he's going to determine what's on the C-terminus. So now he knows the starting point, he knows the ending point, and he knows what everything is in between. He just doesn't know how it's all connected yet. Right? So he's kind of partial way there. The next thing he's going to do is he's going to take a sample of a small amount of his sample, and he's going to subject it to different enzymes. And he's going to see how those enzymes cut that peptide up. And it turns out that if you take a peptide and you feed it to trypsin, trypsin will break it in half, or break it down, I shouldn't say in half, at lysine residues and at arginine residues. It leaves everything else alone. But everywhere there's a lysine or an arginine, it'll cut it, and it'll make a fragment. If he uses chymotrypsin will go along and cut it everywhere there's a phenylalanine, a tyrosine, or a tryptophan. These are rules. These are digestion rules. He will also do pepsin, and he knows that pepsin cleaves at phenylalanine, tyrosine, tryptophan, leucine, aspartic acid, and glutamic acid. Okay? Now he's got a bunch of fragments, and he knows the rules for how these things were broken down. Okay? He might even use cyanogen bromide, which will cleave at methionine. And what he'll do is he'll take each one of these fragments from these different things, and he'll do Edmond degradation over and over again to determine the sequence. Edmond degradation cuts off the N-terminus, right? So he'll take that small fragment, and he'll determine what the N-terminus is, and then he'll take what's left of that, and he'll do it again, and he'll determine the sequence. Okay? And so let's look at a quick sample problem. You are not going to have to do this on the exam, okay? You will do this when you get to biochem. I'll leave it for them, but I want you to be prepared for it. So, Colton determined that his peptide had 20 amino acids. By his amino acid analysis, he determined that he had 2 glycines, 4 alanines, 4 leucines, 3 phenylalanines, a tryptophan, 2 lysines, 2 methionines, a serine, and an arginine. His terminal residue analysis determined that the peptide started at alanine and it ended at phenylalanine. So he knows what his building blocks are, and he knows where to start and where to finish. Right?
It's like a puzzle.
It's like a puzzle with thousands and thousands of combinations. So what does he do? He takes his polypeptide again, and now he does trypsin hydrolysis. And he determines by that he got 4 fragments. He got this fragment, this fragment, this fragment, and this fragment. Okay? He determines that fragment 3 has to be the last 5 amino acids of the sequence. He knows that the very end of this has to end in phenylalanine, right? Because he determined that here, right? And it's at the very end. So these 5 amino acids linked like this have to be at the end of his analysis.
How does he know what's in the fragments?
So he took the fragment and he did an Edmond degradation and determined that the first one was leucine. Then he took what was left and he did another Edmond degradation and determined that it was glycine.
One by one.
One by one, yeah.
Oh, wow.
So you can see why this took people 4 or 5 years to determine, right?
4 or 5 years to doing one?
Huh?
4 or 5 years to doing one, I mean.
Back in the 50s. Yeah. So he does this, right? He does this over and over again. He does this for trypsin. He does this for cyanogen. Wait, what did I miss one? Oh, there we go. Right. So he knows the N-terminus, etc. He knows what these are here. Right. We can't know exactly yet. So he does cyanogen bromide, and it gave 3 fragments, and we know that cyanogen bromide cleaves at methionine only, right? So again, we also know that this is the C-terminus, but now notice there's more amino acids,
Yeah.
right? So now we're starting to build up this fragment a lot more, right? So this must be the N-terminus. So the N-terminus must be alanine, leucine, glycine, methionine, right? And this one, because it has the N-terminus or the C-terminus, couldn't have been that, right? So he knows a lot of this stuff already. So now he starts to assemble these pieces together, and he builds up what he thinks the sequence is, and then he goes through and he mentally digests it again. Okay? So he thinks that this is the sequence, and he goes through and he says, okay, now if I'm trypsin, I'm going to cut here, I'm going to cut here, and I'm going to cut here. Did I get these fragments?
Yeah.
The answer was yes, so that makes sense. He's then going to do the same thing with cyanogen bromide, and he knows that it cuts here and here. Did he end up with those fragments? The answer is yes, right? So he knows that this all makes sense in terms of determining his sequence. That was fast, right?
That's fun.
It's fun. But if you love puzzles, you're going to love biochem with this.
So in terms of our test, where is the last thing that we need to know?
You need to know roughly what's going on here, but I'm not going to give you a problem where you have to determine the sequence. You need to know what trypsin does, you need to know what chymotrypsin does, pepsin, all those types of things will be fair game. So I could give you a protein or peptide and say, where would trypsin cut? I have to show me that.
So
But you're not going to determine the sequence.
You said beginning of class that the fall exam was taken the lowest score, right?
Huh? No, I didn't say that.
Replace the whole-
We could play the whole grade.
the whole grade.
All right, folks, I've got your exams. I'm going to announce your name, and then you can pick it up on your way out. Cassidy? Dakota?
What did you say about
Replaces the total grade. So like if your average grade in the class is like B, but your final grade,
Jenna?
you get an A. Does that make sense?
Haley?
So if you make it, so we have a C right now.
In the class.
I mean,
Bianca?
there's no grade. That
Miranda?
Did we miss the same one?
Colton? Caleb? 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 But you? Caleb or Caleb? Victoria? Jessica? Cindy? Rose? Kimberly? Bailey? Rio? Jason? All right, I'm gonna post it. Kayla? Leah? Kayla? Kate? Sarah Hill? Dallas? Dallas? Misha? Sue? Cassie? Margaret? Madeline? Kate? go.
You don't have another Cassidy, do you? I think she walked out with mine and I had hers. I gave it to her friends though. She's
All I got is Caden.
so she had mine.
Sorry.
Right down. And the, again, I'll cover